Hello, my name is Miles Padgett and I'm PI of QuantIC, one of the UK's 4 quantum technology hubs. QuantIC is pursuing quantum-enhanced imaging. Our mission is to bring quantum technology to bear on real-world imaging challenges across the industrial, scientific, security and consumer markets. QuantIC is a consortia of 8 different UK universities: Glasgow, Strathclyde, Heriot-Watt, Edinburgh, Bristol, Exeter, Imperial College and Southampton. And together we are working with over 40 UK companies trying to use quantum physics to solve imaging challenges. Our technical programme can be divided into 3 different challenge areas. The first of these is seeing through obscuration. That means seeing through things like fog or rain or snow or smoke or even the human body. Our second challenge is using the quantum entanglement to beat the performance of classical imaging systems, specifically around the resolution of an imaging system and indeed its rejection of background noise. And our third challenge area is developing new detector types capable of recording single photon images, either at unusual wavelengths, out with the wavelength range of normal silicon-based technology, or indeed with extreme timing resolution. Our program is centered around the development of many different technology demonstrators, showing how quantum science can be used to beat classical imaging limits. Our demonstrators are then divided into specific market sectors, including transport, life sciences, security and sensors, general detector development, many of which are all underpinned by new computational methods. Taking the first of these areas, namely transport, I've picked out 2 of the demonstrators to illustrate the kind of things that QuantIC is delivering. The first of these demonstrators, by Jonathan Leech and his colleagues at the University of Heriot-Watt, is the application of SPAD cameras. These cameras are made by Robert Henderson at the University of Edinburgh. Whereas a normal camera records the intensity at every single pixel in the image, a SPAD camera measures the arrival time of the first photon. If the scene is illuminated by a pulsed light source, then this arrival time equates to the distance of that pixel in the scene. Therefore, using a SPAD camera, it's possible to record a 3D image. Jonathan Leech and his colleagues Gerald Buller and others have used these cameras to record scenes with hundreds of meters of range, recovering centimeter depth resolution at video frame rates. Such cameras have clear applications in the field of autonomous vehicles. A second area is from one of our new partners, Peter Smith at the University of Southampton. If I restrict myself to working in the visible region of the spectrum, then existing camera technology is extremely sophisticated, both in terms of its sensitivity and indeed its resolution. That becomes more problematic when I move to other wavelengths, such as the shortwave infrared. And these other wavelengths are of interest to me, not least because they allow me to see better through fog, smoke, and other obscurants. Unfortunately, existing cameras in this other wavelength range tend not to be very good. So Peter's approach is to take the light at one wavelength and transform its wavelength into a wavelength which is more readily detected. These wavelength transformations use nonlinear material, often within a waveguide geometry, to get conversion from the infrared into the visible, approaching, up to 44% of the energy. If successful, these kind of devices will allow normal visible cameras to be used to image scenes at different wavelengths, where that wavelength, for example, may be more transmitted by the scene. A second area is the area of life sciences, where we are trying to use quantum physics to improve various imaging methodologies within the life sciences for both biological and clinical applications. The first demonstrator I've picked out is by Daniel Faccio at the University of Glasgow. He, like our colleagues at Heriot-Watt, are using SPAD cameras and indeed single SPAD devices, this time using it to measure the light that is transmitted through the human body. If you hold, for example, your hand up to a bright light, you'll see that light is indeed transmitted, but unfortunately, any resemblance of an image is scrambled by the scattering of the tissue. Daniele and his colleagues, including Rod Murray-Smith, also at the University of Glasgow, has shown that these seemingly random patterns can be inverted through use of photon timing and machine learning, such that the image of any object buried in a tissue-like material can be recovered with a millimetric resolution. Such systems could potentially obtain the same kind of images that one traditionally gets from bulky and expensive MRI machines, but these images in these new systems would be obtained solely using light and cameras. Another area where we are active within the context of QuantIC is one of my own. It is to build ultra-thin endoscopes. Normal endoscopes, of course, are often a centimetre in diameter, but we have shown that it's possible to make an endoscope the width of a single human hair, indeed one single optical fibre. And using these fibres, we are able to recover images, not just in 2D, but in 3D. Here we see some video of an image taken of a person sitting on a stool, several meters distant from the end of the single fibre, and with centimetre or indeed millimetre depth resolution. Such endoscopes, in addition to being relevant to the life sciences, have clearly got applications for general industrial inspection in awkward to reach places. Another market area where we are active is security and sensors. Here we see a video from phase 1 of QuantIC of gas leaking out of a pipe. This was methane gas visualized by using light at 1.6 microns in the shortwave infrared to see the absorption of the gas as it forms a cloud around the pipe. Moving forward, one of the areas that we are active in is led by John Jeffers at the University of Strathclyde and John Rarity at the University of Bristol. They are looking at using quantum light sources to improve both LIDAR and radar systems. As we have discussed already, it is possible to recover a 3D image by using a pulsed light source and then timing of the backscattered light to determine the range. These systems are traditionally based on repetitive pulses from a laser, and as such can be confused by other systems in the vicinity, or indeed deliberately confused if one was trying to mislead the sensor into thinking an object was somewhere else. John Jeffers and John Rarity are instead using quantum light sources, which produce the photon pairs 2 at a time in a random sequence. One photon is used to probe the object, the other photon is a reference. Looking at any one of them on its own, it appears as a random sequence light source. It is only by combining the 2 signals that one can infer the depth data. And as such, these type of systems are resistant to confusion and indeed resistant to being spoofed. Another area where we are using quantum physics is led by Chris Phillips from Imperial and John Rarity from Bristol. They are again using 2 photon sources to image objects, but here the remarkable physics of quantum science means that it is possible to record an image of an object even though the illuminating light has never been detected, never been recorded by a camera of any kind. Since this illuminating light can be a light of essentially any wavelength, this means that I can use these systems again to create opportunities to image things at very unusual wavelengths, while it is the visible light, the other entangled photon, which is detected. And so once again, it is possible, for example, for me to illuminate the scene at 1.6 microns, but then image the data at 800 nanometers, namely that I can use a high-performance visible camera to recover an image in a wavelength region which would otherwise be unobtainable. Many of our systems rely on new forms of detector technology. One example I've mentioned twice already, it's the work of Robert Henderson at the University of Edinburgh, who is designing SPAD cameras. These are the cameras which record the arrival time of individual photons and are the basis of 3D imaging. They are the basis of seeing through obscuration, and indeed can be used for lifetime fluorescence lifetime microscopy. Robert's latest devices are 200 by 100 pixels with timing resolution of picoseconds corresponding to millimeters of depth, with an overall sensor efficiency in excess of 50%. Another area where we are active is in extending the wavelength range of silicon detectors. This is work by Doug Paul, also by Doug Paul at the University of Glasgow, also Gerald Buller again at Heriot-Watt, whereby using germanium overcoating on silicon, it's possible to extend the wavelength range of a silicon-based detector into the shortwave infrared, thereby opening up applications in both LIDAR systems for autonomous vehicles, but also in communication systems. As I've said already, many of these techniques are underpinned by new and important computational methods. One of these areas is Steve McLaughlin at the University of Heriot-Watt. He and his colleagues are taking data from a number of our systems using image priors to denoise them. This is particularly difficult to do in the quantum regime, where the statistics are Poissonian rather than Gaussian, but also by taking on board these inverse methods, this is informing the design of our own imaging systems, such that the combination of system and software can obtain unique performance levels. Another area which I've also referred to is being led by Rod Murray-Smith at the University of Glasgow. This is machine learning. I've referred to already that many optical systems distort an image so badly that the output light is no longer recognizable in any way, shape, or form as the input image. But nevertheless, the pattern is reproducible, the information is hidden in there, and new computational techniques in machine learning allow us to learn these patterns and invert them to recover the true form of the image, a technique which is applicable to many imaging systems, both quantum and indeed classical. So, thank you very much indeed for your attention. I hope in talking about a number of our demonstrators, roughly speaking half of them in the whole program, that I've been able to give you a flavour as to the kind of things and kind of opportunities that the work in QuantIC is enabling. And now I'm very happy to take any questions that you may have. So thank you very much indeed.